Welcome to our deep dive today. We're tackling mathematical proof. It can be a little intimidating sometimes, but it's always fascinating, and we're using a text to guide us. Everything you always wanted to know about mathematics, but didn't even know to ask.pdf. Today, we're really diving into the logic behind the equations.
A lot of people think math is about memorizing formulas and just trusting what they're told. But the real beauty of math is its insistence on proof. It's about establishing truth, using logic and reasoning. And those are skills that are surprisingly useful, even outside the classroom.
So let's start with proof. The text gives a bunch of different proofs for the Pythagorean theorem. Remember that one from school? A squared plus b squared equals c squared. Some are pretty convincing, but there's one that's just hilarious. It basically says, well, the theorem must be true because teachers wouldn't lie to us.
Right. And that's a great example of why mathematicians are so picky about what makes a good proof. Just seeing a pattern or relying on someone's authority, it's not enough. A true mathematical proof has to demonstrate that something is always true, no matter what. It has to be correct. Using logic flawlessly, it needs to be precise, using mathematical language carefully, and it needs to be clear. So anyone with a basic understanding can follow the reasoning.
So it's like building an argument where every brick is solid and perfectly in place, leaving no room for doubt. But this is where it gets really interesting for me. The text describes mathematical proofs as a game with specific rules and strategies, like a mental chess match.
Absolutely. And like any game, there are specific notations and moves you need to learn. We're going to look at logical notation, specifically quantifiers. Don't worry, they sound more intimidating than they
I
are.
swear this sounds like something out of Star Trek.
Well, imagine you want to say something is true for every single number. Instead of writing all that out every time, mathematicians use a symbol. It looks like an upside-down A. That symbol means for all. There's another one, backwards E. It means there exists, the shortcuts, to express powerful ideas.
So if I wanted to say, for every number, there's a bigger number, there's a quick, elegant way to write that.
Exactly. And once you understand these symbols, you can start building more complex arguments, using different strategies, like direct proof, proof by contradiction, and even finding those sneaky exceptions called counterexamples to debunk a claim.
Let's talk about a specific proof technique. Induction. The text uses a brilliant analogy, the domino effect. If you knock over the first domino, and each falling domino knocks over the next one, then all the dominoes will fall.
That's a great way to visualize induction. You start by proving a statement is true for the first case, like that first domino. Then you show that if the statement is true for any case, it must be true for the next one. This creates a chain reaction, proving the statement for an infinite number of cases.
I actually used to dread induction proofs in school, but the domino thing makes it click. It feels like something that could apply to the real world, not just abstract math problems.
You're absolutely right. Induction is used all the time in computer science, economics, even analyzing things like how trends spread on social media. And there's a variation on induction. It's called the minimal criminal technique, like detective work. You prove something can't be true by showing it would lead to an impossible first case.
That sounds intriguing. Okay. Ready to explore sets and relations and the mind-bending world of modular arithmetic, I'll admit. When I saw those terms, I thought we were in for a dry lecture.
I think you'll be surprised. We'll start with the basics, sets and relations, and how we can group things based on shared properties. Then we'll dive into modular arithmetic, which is basically the math of remainders.
The math of leftovers, how is that useful?
It might sound a little odd, but modular arithmetic is used in all sorts of ways. Think about a clock. It's a perfect example of modular arithmetic. Instead of numbers continuing infinitely, they wrap around. This kind of math is what makes online encryption work, keeps your data safe. And it pops up in unexpected places, like music theory. It's like a secret code, based on remainders instead of the whole number.
Okay. I'm starting to see how this wraparound math could be useful. What else can we do with it?
Well, we can explore something called multiplicative inverses, which work differently in modular arithmetic. It's kind of like finding a secret key that lets you solve equations in this unique number system. And then there's the Chinese remainder theorem. It's a really powerful tool for breaking down complex problems into smaller, easier to solve parts.
So modular arithmetic isn't just about clock faces and remainders, it's a whole system with its own rules and tools for problem solving.
Exactly. Now, are you ready for something that might truly bend your mind? Let's talk about functions and cardinality.
Bring it on. When I skimmed through the text and saw cardinality, I thought, isn't that just a fancy word for counting?
It is about counting, but on a whole different level. We're going to explore the size of sets including infinite sets, which is where things get really interesting.
Okay, I remember learning about infinite sets, but the text says there are infinite sets of different sizes. That feels like it breaks the whole concept of infinity. How can one infinity be bigger than another?
It's a mind-blowing idea, right?
Yeah.
That's where a proof called Cantor's diagonalization argument comes in. It demonstrates that the set of real numbers, think of all the numbers on a number line, is actually bigger than the set of natural numbers, which is just 1, 2, 3, and so on.
So there are different levels of infinity. That's wild. Okay, let's move on to something that sounds a little more down to earth. Combinatorics, the art of counting. I have a feeling this is about more than just adding and subtracting.
You're right. Combinatorics is all about figuring out how many different ways you can arrange or select things from a set. It's incredibly useful in everyday life. Imagine you're choosing an outfit, putting together a team, or even cracking a code. Combinatorics provides the tools to calculate all the possibilities.
I'm starting to see how this could get complex quickly. Where do we even begin with figuring out all those possibilities?
Well, we can start with some fundamental principles, like the
Okay.
rule of sum and the rule of product. These are like our basic building blocks for counting.
Give me an example. How would these rules help me make a decision?
Think about ordering food. The rule of sum says, if you're choosing between a burger or a pizza, you add the number of burger options to the number of pizza options to get your total choices. But the rule of product comes in. When you're choosing a burger, A and D fries, A and D to drink, then you multiply the number of options for each to find all the possible combinations.
So the rule of sum is like making one choice from different categories. And the rule of product is for when you're making multiple choices together. It's like building a meal versus just picking one dish.
Exactly. And then there are arrangements and selections. This is all about understanding whether the order you choose things matters. Like with a license plate, the order of the letters and numbers is crucial. But if you're dealt a hand of cards, the order you got them doesn't change the hand itself.
That makes sense. So sometimes order matters, and sometimes it doesn't. Is there a special technique for figuring out all these arrangements?
There is. It's called counting in two ways. It's a proof technique, where you prove an equation is true by showing that both sides of the equation are just counting the same set of objects, but in different ways. It's like double-checking your money.
Right.
By counting your bills and then your coins, the total's the same, even though you count it differently. The text gives a really neat example called the hockey stick identity to illustrate this.
I love that. Counting in two ways. It sounds almost like a magic trick, but it's really about finding different paths to the same truth.
Precisely. It highlights the beauty of mathematical thinking. There are often multiple ways to arrive at a solution.
You know, as we go through all these different areas of math, from proofs to sets to combinatorics, it's striking how interconnected it all is. It's like they're all different pieces of the same puzzle.
That's a great observation, and that's one of the most rewarding aspects of studying math. It's not just a collection of isolated facts and formulas. It's a beautifully interconnected system of logic and reasoning.
Speaking of logic, the text mentions that sometimes. You can start working on a math problem without realizing it's actually impossible to solve. It's like setting off on a quest with a map that leads nowhere. How can we avoid falling into that trap?
That's where having a deep understanding of the fundamental rules and axioms of mathematics comes in. It's about knowing the limits of what's possible, the boundaries of the mathematical universe. Sometimes a seemingly simple problem might actually be unsolvable, or a statement might be impossible to prove or disprove.
So it's not just about finding the answers, it's about knowing which questions to ask in the first place.
Exactly. And then there's the concept of if and only if, a phrase that signifies logical equivalence. The text gives a great analogy. With buying a new car if you win the lottery, versus buying a new car only if you win the lottery. It seems like a small difference, but it has huge implications.
So if means one thing could lead to another, but if and only if means those two things are completely bound together, like two sides of the same coin.
That's a great way to put it. Understanding if and only if is crucial for building strong mathematical arguments and seeing the exact relationships between different mathematical statements. It's like a test of true equality. In the world of logic,
Okay, I think I'm getting that. Is there anything else we need to know about the language of logic? Any other tricky phrases to watch out for?
well, we should talk about logical negation, which is basically how to say not in a mathematically precise way. It might seem simple, but when you're dealing with complex statements that use those quantifiers we talked about earlier, for all and there exists, things can get tricky.
So it's easy to say not to a simple statement. But when you have a statement that's saying something is true for all numbers, or that there exists a specific number, negating that correctly gets more complicated.
Exactly. It's like trying to untangle a complicated knot. You have to carefully reverse every twist and turn. The text provides some great examples of how to negate those complex quantified statements, emphasizing how important precision is. Even a tiny knot in the wrong place can completely change the meaning of a statement.
This deep dive is really opening my eyes to the power and precision of mathematical language. It's like learning a whole new way to think and communicate. But it's not all about abstract symbols and logic, right? This stuff actually has real-world applications.
Absolutely. The skills you develop by studying math, logical thinking, careful analysis, clear communication, those are valuable in any field, whether you're writing a report, building an argument, or even just making a decision. These skills can make you a more effective thinker and communicator.
It's interesting. The text even talks about bad proofs being valuable. I remember that one. That tried to show 0 equals 36. I was following along and it seemed so convincing. But then there was this tiny error, and the whole thing fell apart.
Right. Those kinds of bad proofs are actually great learning tools. They force you to sharpen your critical thinking skills and really understand the rules of logic. By dissecting where those proofs go wrong, you gain a deeper appreciation for precision and how easy it is to make a subtle mistake. That can throw off your entire argument.
It's like learning from your mistakes. But even better, you're learning from other people's mistakes without having to make them yourself. Speaking of learning, the text emphasizes how important clarity is in a good proof. It's not enough for a proof to be logically correct. It also needs to be communicated clearly.
Exactly. A good proof should guide the reader through the argument, making sure each step is easy to follow and understand. It's like writing a good story. You want to take the reader on a journey, making sure they don't get lost along the way. And that's a skill that goes way beyond mathematics. Being able to explain complex ideas in a clear and understandable way is crucial in any field.
This deep dive has been a real eye-opener for me. I used to think math was just about memorizing formulas and solving equations, but now I'm seeing it as this incredible system of logic and reasoning that has applications everywhere. What's the biggest takeaway you want our listener to walk away with?
I'd say the biggest takeaway is that mathematics is more than just numbers and symbols. It's a way of thinking, a powerful tool for understanding and engaging with the world around us by developing our mathematical skills. We're not just learning how to solve equations. We're learning how to think more critically, analyze information more effectively, and communicate our ideas more clearly.
That's a fantastic point to end on. Thanks for joining us on this deep dive into the world of mathematics. Until next time, keep those minds curious and those arguments sharp.
Absolutely. The skills you develop by studying math, logical thinking, careful analysis, clear communication, those are valuable in any field, whether you're writing a report, building an argument, or even just making a decision. These skills can make you a more effective thinker and communicator.
You know, it's interesting. The text even talks about bad proofs being valuable. I remember that one that tried to show 0 equals 36. I was following along and it seemed so convincing. But then there was this tiny error.
Yeah.
And the whole thing fell apart.
Right? Those kinds of bad proofs are actually great learning tools. They force you to sharpen your critical thinking skills and really understand the rules of logic. By dissecting where those proofs go wrong, you gain a deeper appreciation for precision and how easy it is to make a subtle mistake. That can throw off your entire argument.
Yeah, it's like learning from your mistakes. But even better, you learn from other people's mistakes without having to make them yourself. Speaking of learning, the text emphasizes how important clarity is in a good proof. It's not enough for a proof to be logically correct. It also needs to be communicated clearly.
Exactly. A good proof should guide the reader through the argument, making sure each step is easy to follow and understand. It's like writing a good story. You want to take the reader on a journey and make sure they don't get lost along the way. And that's a skill that goes way beyond mathematics, being able to explain complex ideas in a clear and understandable way is crucial in any field.
This deep dive has been a real eye-opener for me. I used to think math was just about memorizing formulas and solving equations. But now I'm seeing it as this incredible system of logic and reasoning that has applications everywhere. What's the biggest takeaway you want our listener to walk away with?
I'd say the biggest takeaway is that mathematics is more than just numbers and symbols. It's a way of thinking, a powerful tool for understanding and engaging with the world around us. By developing our mathematical skills, we're not just learning how to solve equations, we're learning how to think more critically analyze information more effectively, and communicate our ideas more clearly.
That's a fantastic point to end on. Thanks for joining us on this deep dive into the world of mathematics. Until next time, keep those minds curious and those arguments sharp.